Traditional functional safety, governed by ISO 26262, manages random hardware faults and deterministic software errors. Here, safety is guaranteed through verifying precise, rigid logic gates. Machine learning removes explicit code. When a 3D LiDAR point cloud flows into a neural network, behavior is determined entirely by the training data. This shift creates a critical gap covered by the ISO 21448 standard, known as SOTIF. SOTIF addresses the safety of the intended functionality, focusing on hazards caused by performance limitations or missing specifications in the training data. To bridge this gap, ISO PAS 8800 Clause 11 formally elevates the dataset from a passive resource to an active, auditable safety artifact. Managing AI safety requires treating the data pipeline with the same rigorous, verifiable architectural standards applied to physical components like a braking system. We can examine this lifecycle through an automatic emergency braking, or AEB, system operating in heavy rain at night. The safety mandate for this specific ODD requires the AEB system to recognize pedestrians with 99% accuracy at a 30-meter distance. ODD, or Operational Design Domain, defines the specific environmental conditions where the system is certified to function. This V-model diagram provides the structural foundation. The left axis manages design and implementation, while the right handles testing and integration. ISO PAS 8800 maps a strict 7-stage data cycle here, assigning data preparation to the left and safety assurance to the right. Deploying a compliant AEB system requires moving sequentially through this pipeline to generate a mathematically defensible safety argument for regulators. The process begins at Step 1, Safety Analysis. Here, engineers identify the specific hazard, AEB failure caused by poor nighttime pedestrian recognition. At Step 2, Requirements, this hazard is translated into technical constraints focused on sufficiency and diversity. This defines exactly how much data is needed to cover the range of possible environmental variables. To satisfy the safety goal, the distribution matrix must meet specific metrics. 15% of the million-image dataset must be nighttime rain scenarios, with 50,000 umbrella samples. Simultaneously, logical requirements enforce versioning and access controls, preventing unauthorized data modification. These requirements ensure the dataset mathematically covers the target operational design domain on paper before a physical sensor is ever activated. At Step 3, Design, engineers establish the strategy to acquire that 15% distribution target. While physical data collection provides real-world sensor noise, it is often too inefficient to capture rare edge cases through driving alone. Data augmentation techniques bridge this gap. Using deep learning style transfer, teams can computationally inject water drop noise and contrast reduction into existing clear weather footage. For high-risk scenarios, we use synthetic data generation. This safely simulates events like a child stepping into a roadway under heavy rain and low light. Step 4, Implementation, introduces a significant point of failure. This phase involves manual data labeling, which is inherently prone to human error. To mitigate this, teams apply an FMEA framework directly to the human labeling process. This identifies potential labeling errors before they are ingested by the model. For our AEB case, this results in a rigid labeling rule. The bounding box must explicitly include both the tip of the umbrella and the pedestrian's feet. Without these exacting labeling guidelines, the model will ingest a flawed ground truth, rendering even a large and diverse dataset unsafe for real-world use. Moving to the right side of the V model requires a distinction between two often confused processes, data accuracy and system safety. Step 5 is dataset verification, a static check confirming the dataset matches initial requirements. Automated checks verify the 15% nighttime distribution and umbrella bounding boxes. Step 6 is validation. A dynamic hardware-in-the-loop simulation runs the model in a complete system. In validation, we deploy the AEB model into a wet track integration test to observe if the vehicle actually issues a timely braking command when encountering a pedestrian. Verification asks, did we build the data right? Validation asks, did we build the right data for the safety goal? A dataset can pass every statistical check in verification, but still fail validation if the initial requirements failed to capture the true physical complexity of the hazard. Step 7. Maintenance establishes that commercial deployment is the beginning of a continuous feedback loop rather than the end of the project. After launch, a vehicle will eventually encounter a scenario not covered in training, such as an electric scooter rider at night. This is out-of-distribution, or OOD, data. The neural network was not trained on this specific geometric signature, leading to high statistical uncertainty. When the system detects this uncertainty, it must trigger a functional safety fallback mechanism and capture the OOD sensor data for analysis. This capture field anomaly bends the V model into a circle. The data packet is routed back to Step 1 to update labeling guidelines and expand the operational design domain. The model is retrained with the new e-scooter data, passes through the V&V process again, and is deployed to the fleet via an over-the-air update. ISO PAS 8800 transforms data management into a systematic engineering engine, a continuous flywheel that converts unknown hazards into known safety.